Okay, next we talk about the receptors. We have seen that in a cell there are two kinds of receptors. If the signal can pass through the plasma membrane, it is recognized here in the cytosol by the nuclear receptor. If it cannot pass through the plasma membrane, it is recognized here on the cell surface, and we call them cell surface receptors. Now, we are going to see three kinds of cell surface receptors. One is the ion channel coupled receptor. Okay. And two, it is the G protein coupled receptor, which is also called GPCR. And three, they are the enzyme coupled receptors. And of course, each of these class contains large amount of receptors. They can work for several different things, but at the end, each surface receptor belongs one of these three classes. So let's say the first one, the ion channel coupled receptors. So when they recognize the signals, when the signal interacts on the target surface, and we know that they are matching really good, the ion channel opens. Now, once the ion channel opens, the ions move from one side to the other side. Here, they move from the extracellular environment to the cytosol, but the opposite is also quite possible. They can move from cytosol to the extracellular environment. But in every case, because the ions are moving, it creates a current. And at the same time, it alters the membrane potential. Now, there are three classes of them: ion channel, GPCR, the enzyme coupled. Out of these three, the ion channel coupled receptors, they are the fastest ones. Because ions are very small, they are moving fast. This is why when they move quite fast, once the channel is open, they modify the membrane potential extremely fast, and this modified membrane potential is a very quick response. This is why in the neurons, between the two neurons, I should say, let's say this is a dendrite, this is the axon terminals, and another neuron with the dendrites, another axon terminal. The synapse between the two of them has the ion channel coupled receptors. Let's don't draw it this way, let's draw it better. So, of course, there's a synaptic terminal, of course, there's a postsynaptic site, and there are signals that is expressed from here, and that signal has to be received on the postsynaptic surface. And the receptor that is on the postsynaptic surface is most possibly an ion channel coupled receptor. These are also called ligand-gated receptors or transmitter-gated ion channels. Now, when the signal binds there, this ion channel is going to open. Think that it's a sodium channel. The channel is going to open and the sodium is going to rush in, so it is going to create a depolarization. And depolarization means it's going to help going above the threshold and exiting the threshold, it can create an action potential. Or if it's, for example, a potassium channel, the potassiums are going to leak out, so it doesn't help. Or if it's a chloride channel, it's going to create a hyperpolarization. And we know that the hyperpolarization cannot create an action potential. It's rather going to prevent an action potential from happening. But in each case, this is a very fast interaction. This is the very fast kind of cell-to-cell interaction. So the cell surface, the ligand-gated ion channels or the ion channel coupled receptors are the fastest way of converting an extracellular signal into a cellular signal. So this is the fastest signal transduction. Okay? This is why neurons prefer them. Of course, this is not the only thing that is happening in the neurons. Neurons also use the GPCRs, but they are used for the long-term effects like the long-term potentiation, long-term depression. They're also used for the architecture of the synapses. But for the fast signals to decide on the action potential, the ion channel coupled receptors are preferred. Now, the second class is the G protein coupled receptors, and this is a very, very ancient way, and virtually all the organisms, not all the organisms in the world, but most of the organisms in the world have the G protein coupled receptors. We call them G protein coupled receptors because the G proteins were discovered first, but actually GPCRs evolved first and then G proteins evolved. So in our body, the GPCRs and the G proteins are working together, but there are bacteria which doesn't have any kind of G protein, but they have the GPCR, so we know that the GPCRs can work themselves without the help of the G protein. So the basic working mechanism is that there is a G protein, let's make it a nice color. There is this G protein coupled receptor, there is the G protein, and currently they are both inactive. Now, when the signal molecule joins, which is here, the G protein becomes active. And once it's active, it goes and interacts with something else, and this something else relays the signal. So at the beginning, it was an extracellular signal, and now it's an intracellular signal. This is how the signal is transduced. This is how the signal became an internal signal. Now it's going to move in the intracellular site. And I can say that this is the slowest one. But also, this is very common. In all the branches of life, it's quite used. For anything that you think of, for any kind of mechanism you think of, GPCRs are used. And the last one is the enzyme coupled receptors. Here, when we are talking about G protein coupled receptors, neither the receptor nor the G protein are enzymes. There are no enzymes here. This is an enzyme. An enzyme only joins in the third step, or maybe even more. But here in this case, either the receptor itself is an enzyme like this, or it directly interacts with an enzyme like this. So in this case, the enzyme coupled receptors are faster than the GPCRs, but they are slower than the ligand gated ion channels. So when the extracellular signal comes, they usually dimerize. Most of the enzyme coupled receptors, they don't work alone, they usually work in couples, and then they start an enzymatic activity, and this enzymatic activity is related to the intracellular site, so the information is internal now. Now, we are going to start, we have some examples, sorry. And then we are going to start to see the G protein coupled receptors. Okay, so many things that we use in our daily life, many things that affect our lives, they are acting on the cell surface receptor, because the cell surface receptors are how we perceive the extracellular environment. A cell can understand what is going on around only and only using its receptor. As I said, the cells have no eyes, no ears, no hands. The only way that they can interact with the extracellular environment or outside is these receptors. I mean, it should use one of these three receptors so it can understand what is going on around. So if we use some chemicals, if you use some materials, we can actually change how our body perceives the cell, or perceives what is going on around. For example, maybe you have heard of Valium. It was a very popular antidepressant previously. And we know that the Valium is stimulating the GABAergic signaling. Now, GABAergic signaling is actually acting on these kind of ion channel coupled receptors. In this case, the signal molecule is normally GABA in normal case, but Valium is mimicking that. So instead of GABA, Valium is binding there. So GABA is not here anymore. Instead, we have Valium. And this Valium is opening channels, but this time the channel is a chloride channel. And because it's a chloride channel, it's hyperpolarizing the membrane. And because it's hyperpolarizing the membrane, the people using Valium have less action potential. Instead of having more and more neural activity, maybe they are angry, maybe they are excited or something. When they use Valium, they are going to have hyperpolarization, which means they are going to have more difficult action potential. so they will be more like sleepy, they will be calm, maybe more happy. And today we know that it has many other side effects, but this is how the Valium works. It acts on the ligand-gated ion channels. And the second thing is cigarettes. I really hope that there are no smokers in you. Smoking kills. And the active material here is the nicotine. This. And what nicotine mimics is acetylcholine. Okay, we didn't see neurobiology, but I can say that acetylcholine is the main neurotransmitter for the neuromuscular junctions. And the neuromuscular junctions are the synapses that are activating the muscles. So how we use our muscles, how we control our muscles are through these junctions, through these synapses. So each time when you want to use your muscle, when you want to talk or move your finger, acetylcholine is secreted in the neuromuscular junction. And in this case, the nicotine is mimicking acetylcholine. So the acetylcholine activated ion channel coupled receptor opens. And in this case, what it really affects primarily is the blood vessels. It constricts the blood vessels. Remember, the blood vessels can be small or big. When it is small, less blood flows, but the pressure increases. And when the blood vessels dilate, more blood flows, but the pressure decreases. So because it constricts the blood vessel, it increases the blood pressure and people like it. Of course, it gives other pleasures in other parts of the body, but this is one of the first outcomes. Third, heroin. Okay, I really hope that nobody smokes, and I really hope that nobody uses heroin in our class, because it's, too dangerous. You cannot quit it. Okay, this heroin, morphine and heroin, it mimics endorphin and enkephalins, and they're acting on GPCRs, G protein coupled receptors, like this. So in this case, the signal molecule is heroin instead of endorphin, and it activates the G protein coupled receptors, which is an opioid receptor. And at the end, it gives analgesia, which is the relief of pain in the case of morphine, and it gives euphoria in the case of heroin. Euphoria means being very happy, being extremely good. And we know that another pathway, another thing that activates this same GPCR is feeling love from your mother. So the mother love activates this GPCRs in your brain and makes you extremely happy. But if you cannot find mother love, maybe people are using heroin because of that. They can activate the same subclass of the GPCR so that they feel euphoria. Okay, another example is curare. So it is used by some tribes for hunting, because what curare does is that it doesn't activate, it doesn't stimulate or mimic of course it mimics, but it doesn't stimulate the neuromuscular junction. It blocks the neuromuscular junction. So it behaves like acetylcholine, like in this case. But instead of activating it, it blocks the ion channel. So the ion channel will not be reactive anymore. And because the neuromuscular junctions are not moving, are not useful anymore, the person or the animal goes under paralysis. But this paralysis is, again, can be cured with some certain chemicals. So if you can remove the curare, you can deal with it. If not, you're in trouble. And of course, when they are fighting, when they're in war, or when they are hunting animals, they use this. It can be very helpful for them. Another thing is strychnine. Here, it was a highly used poison. Now it's forbidden. We don't use them against rats anymore. And the strychnine mimics glycine. And normally, glycine is another inhibitory neurotransmitter. It is acting on ion channel coupled receptors. And when glycine is not active anymore, when it blocks these inhibitory synapses, just the opposite of this. So these two are opposites. here it creates paralysis, and here it creates seizures. It's a very painful death. I mean, I have seen rats given strychnine because their inhibitory pathways are not active anymore. They are not paralyzed. Their muscles are contracting continuously. They have these neural signals continuously. It seems extremely bad. I'm glad that we don't have it anymore. Okay, and there are two other things. I love both of them. One of them is hot pepper. It contains capsaicin, and capsaicin is actually mimicking heat. So it is not mimicking a chemical, it mimics high temperature. Well, there are ion channel coupled receptors in our body that are not activated by chemicals. So they are not receiving chemicals, they are not changing shape with the ligand, but they are changing shape with the high temperature. So when you use capsaicin, you can actually activate these ligand channels, these ligand gated channels or temperature gated channels. This is why we call it hot. And to be honest, your tissues cannot really understand if you are eating hot pepper or if you are drinking hot water. The temperature cannot be discriminated from the spicy hot because they're activating exactly the same molecules. So unless you have some other information like the liquid that you feel on your mouth, you really don't understand if it is hot weather or a high temperature or capsaicin. And this is mint. Mint it has the opposite effect, and it's actually working more or less in the same way. There are some other ion channels. These are ion channel coupled receptors, and they are activated not by hot, but by cold. So when you have mint, when you have these mint candies, you feel cold, you feel refreshed because it is activating the cold sensitive ion channels. This is why you feel cold, and to be honest, again, your cells cannot discriminate if you're really feeling cold or if you're eating mint. There is no extra way to say, okay, unless it is aided by some taste or something, you cannot say the difference. So we can easily mimic chemicals or signals, and we can easily fool our channels. These channels, well, fooling these channels are sometimes very good because this is also how the pharmacology is working. Many of the pharmacological agents, they are just mimicking something. They're just trying to activate or inactivate some receptors. This is how we are curing people in many tissues for many cases.